An atom consists of three subatomic particles, electrons, protons and neutrons. Confined within the nucleus, protons and neutrons are shielded from direct interaction with other atoms. Moving in different shells, subshells and orbitals around the nucleus, electrons create most of the atom's volume. Electrons, particularly those in the outermost shell, drive an element's chemical properties, bonding and reactivity. This is why chemistry focuses primarily on electrons and their arrangement, known as the electronic configuration. This video explores electronic configuration in detail. Hi everyone, this is Akhilanand Singh. In this video, we learn about the electronic configuration of elements. We see how electrons are arranged in different shells, subshells and orbitals and discover rules and principles governing the electronic configurations. Let's get started. Electrons are much lighter and less tightly bound than protons and neutrons. They enjoy greater freedom of movement. They zip around the nucleus in a 3D space occupying different shells as shown in the diagram. A small atom like hydrogen has only one shell. Larger atoms have many shells. Each shell is identified by a number. The shell closest to the nucleus is numbered 1 and it is the lowest energy level. The shell next to it is numbered 2. The shell encompassing shell 2 is numbered 3 and so on. Shells are also referenced by the letters K, L, M and N, where the letter K represents the shell number 1, letter L represents the shell number 2 and so on. The outermost shell is also called valence shell. Electrons in valence shell are called valence electrons, who are responsible for the most of the chemical behavior of atoms. The space inside a shell is further divided into subshells. Subshells are identified by letters such as S, P, D and F. The first shell K has only one subshell S. We write one S to indicate the subshell S within the shell 1. The second shell L contains two subshells S and P. We indicate them by notation 2S and 2P, where 2 signifies the shell number 2. The third shell M contains three subshells S, P and D. We write them as 3S, 3P and 3D, where 3 indicates the shell number 3. The fourth shell N contains 4 subshells S, P, D and F. We write them as 4S, 4P, 4D and 4F. Electronic configuration is nothing but the distribution of electrons in different shells and subshells. The Aufbau principle gives the order of electron filling in an atom. The word Aufbau has German origins. Its root word is Aufbau Principle, which roughly translates to a principle to construct or a principle to build up. It states that electrons fill shells and subshells in order of increasing energy level, starting with the lowest shell and subshell within that. Electrons first fill in all the subshells of a lower shell and then they proceed to next shell's subshells. Let's write the electronic configuration of elements starting with the very first element in the periodic table. We will be filling up the subshells in the natural order such as 1s, 2s, 2p, 3s, 3p, etc. We will get to understand the final details of the Aufbau principle as we move towards the higher elements in the table. A hydrogen atom is the simplest one. It has only one electron which is easily accommodated in the only subshell S of the first shell. So the electronic configuration of hydrogen is written as 1s1, where 1 indicates the shell, S indicates the subshell within the shell, and the superscript 1 indicates the number of electrons. A helium atom has 2 electrons, which also happily fit into the 1s subshell, making its electronic configuration as 1s2. Lithium's atomic number is 3, so it has 3 electrons. The first 2 electrons completely fill in the 1s subshell, so the third electron goes into the next available space, that is the 2s subshell, and its electronic configuration becomes 1s2, 2s1. The next element, beryllium, has 4 electrons and its electronic configuration is 1s2, 2s2. Boron has 5 electrons. Its first 4 electrons go into the 1s and 2s subshells, filling them completely. The fifth electron goes into the next subshell 2p, making its electronic configuration as 1s2, 2s2, 2p1. The subshell P has the capacity to hold maximum 6 electrons. So the next 5 elements distribute their electrons as per the following configuration. Carbon 1s2, 2s2, 2p2, nitrogen 1s2, 2s2, 2p3, oxygen 1s2, 2s2, 2p4, fluorine 1s2, 2s2, 2p5 and neon 1s2, 2s2, 2p6. With this, we have completed the electronic configuration of all the elements of the first 2 periods of the periodic table. We enter the third period with the element sodium, whose atomic number is 11. For sodium, the first 10 electrons would completely fill in the subshells 1s, 2s and 2p. Its 11th electron goes into the next available subshell 3s. This makes the electronic configuration of sodium as 1s2, 2s2, 2p6, 3s1. Similarly, the next element magnesium's electronic configuration would be 1s2, 2s2, 2p6, 3s2. The next 6 elements electrons will increasingly fill in the 3p subshell and their electronic configurations will be accordingly written as the following. Aluminium 1s2, 2s2, 2p6, 3s2, 3p1. Silicon 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur 1s2, 2s2, 2p6, 3s2, 3p4. Chlorine 1s2, 2s2, 2p6, 3s2, 3p5. And argon 1s2, 2s2, 2p6, 3s2, 3p6. Potassium is the next element in the periodic table. Its atomic number is 19. The first 18 electrons of the potassium atom would completely fill in the subshells up to 3p. Where will the 19th electron go? We can expect it to go to the subshell 3d as the shell 3 has 3 subshells S, P and D. But it actually goes into the subshell 4s. Why? To answer this question, we need to give a closer look at the Aufbau principle and understand the n plus L rule built into it. The n plus L rule provides a more accurate guidance to correctly distribute electrons into different subshells. We have been unknowingly following this rule for the elements up to the atomic number 18 when we filled in the electrons into subshells 1s, 2s, 2p, 3s and 3p. But now we really need to understand this rule correctly to populate subshells with electrons beyond the element 18. As per the n plus L rule, the subshell with the lower n plus L value will be filled first. Here n stands for the principal quantum number, which is nothing but the shell number, and L stands for the azimuthal quantum number, which is subshell's numeric value. Subshells S, P, D and F have the numeric values of 0, 1, 2 and 3 respectively. Let us calculate the n plus L value for the subshells 3D and 4s. For the subshell 3D, n is 3 and L is the subshell D's numeric value 2, making its n plus L value as 3 plus 2, 5. For the subshell 4s, n is 4 and L is subshell S's numeric value 0. This makes its n plus L value as 4 plus 0, 4. We can see that the subshell 4s has a lower n plus L value than the subshell 3D. So the subshell 4s will be populated first. That's why the final electron of the element potassium will go into the subshell 4s, not in 3D, making its electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. There is a second part of the n plus L rule as well. It says that when two subshells n plus L values tally, the subshell with the lower n value will be filled first. For example, the subshells 2p and 3s have exactly the same n plus L value of 3. In this case, the subshell 2p will be filled first because it has a lesser n value. You must have realized by now that at times the electron filling order becomes quite strange. It is also very difficult to recall. The diagram on your screen saves us from this trouble. It nicely presents the correct order of filling of electrons into subshells, keeping in mind the n plus L rule. To know the correct order of subshells for electron filling, you just need to follow the arrow from the top in the diagram. As per this diagram, the correct electron filling order in subshells would be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. Henceforth, we'll be using this electron filling diagram in writing the electronic configuration for rest of the elements. After understanding the electron filling diagram, we can easily write the electronic configuration of rest of the elements of the period 4. You can see them on the screen. The configurations of chromium and copper are remarkable. Their strange configurations are a speciality of several d block elements. A similar behavior is common in many elements of the F block too. For d block elements, a half-filled or fully filled d subshell is more stable than a partially filled one. Due to this, the 3d subshell of chromium pulls one electron from the nearest 4s subshell and becomes half-filled. In case of copper, its 3d subshell steals one electron from the nearest 4s subshell to be fully filled. You might have realized that the electronic configuration of elements with higher atomic number becomes quite long and untidy. There is a shorthand notation that uses the symbol of the nearest noble gas in a square bracket followed by the configuration of the valence electrons. For example, the electronic configuration of potassium can also be written as argon 4s1, where Ar in square brackets indicates the electronic configuration of the nearest noble gas argon. In the same way, chlorine shorthand configuration can be written as neon 3s2 3p5. You can see a list of electronic configurations in both the regular form and the shorthand form. This list shows noble gases in green color. In the electronic configurations written so far, we learnt how to show electrons in different shells and subshells. We did not care how the electrons are arranged within a subshell, but sometimes we need to show how each electron is placed in orbitals. Atomic orbitals are regions within subshells where electrons are most likely to be found. Subshells S, P, D and F have different number of orbitals and the shapes of these orbitals also vary. The subshell S has only one orbital which is spherical in shape. The subshell P has three dumbbell-shaped orbitals named Px, Py and Pz with two lobes on either side of the nucleus. The subshell D has 5 orbitals. 4 of the 5 d orbitals have a clover leaf shape, while the fifth is shaped like a dumbbell with a donut around the middle. The subshell F has 7 orbitals. They are of a very complex, multi-lobed shape. In a detailed electronic configuration, orbitals within the subshells sp, d and f are represented by small boxes of square shape. Each such box has the maximum capacity of holding 2 electrons. Since the subshell S has only one orbital, it is shown with a single box. 3 boxes kept together represent the 3 orbitals of the subshell P. These 3 boxes can contain a maximum of 6 electrons. In the same way, the 5 orbitals of the subshell D are represented by 5 boxes kept together, who have the collective capacity of holding maximum 10 electrons. The 7 orbitals belonging to the subshell F are displayed as 7 boxes, who have room for 14 electrons altogether. When we write a detailed electronic configuration, we need to bear in mind 2 rules related to how electrons get placed in orbitals within a subshell. The first rule is called Hund's rule. It states that when electrons occupy orbitals of the same subshell, they first fill it in a singly manner before pairing up. See the example of electrons filling into a carbon atom. When the last 2 electrons try to fill in the p orbitals, the orbitals px and py get 1 electron each. In the oxygen atom, the last 4 electrons try to fill the p orbitals. The orbitals px, py and pz first get 1 electron each following Hund's rule. Then the last electron goes into a px orbital where it pairs up. Pauli Exclusion Principle. An orbital can hold a maximum of 2 electrons with opposite spins. While filling up the orbitals in the oxygen atom, the earth electron pairs up with the 5th electron and it assumes an opposite spin direction. With this, we have reached the end of this video. In the last few minutes, we learned how to write the configuration of electrons in various shells, subshells and orbitals. In the next video, we discover how the periodic table can also be used to write electronic configurations. Thank you.